This is lecture 24, and I think last time when we stopped, we had derived this expression SL equal to square root of minus 2 alpha into nu plus 1 into m dot f triple prime bar divided by rho u. So, we had done that, and of course, there were some questions as to how to evaluate this. We want to evaluate this to be able to calculate SL and then get an idea of the property of the mixture, which is laminar burning velocity. Now, to do this, we identified that the easier part is to calculate, let us say, rho u, then also to calculate nu. Nu is the oxidizer to fuel mass ratio, and also to calculate alpha. We thought that alpha may not be that difficult, but more difficult will be m dot f triple prime bar. And I think the way to learn this is to look up some example from Turns's book in chapter 8. So, I trust that much of it you can do yourself, but I will just spend 1 or 2 minutes on this. M dot f triple prime bar is an omega dot f bar into Wf. Now, omega dot f is the reaction rate of the fuel, and that is actually ddt of concentration of fuel. And just as a specific example, I wrote ddt of concentration of propane C3H8. So, remember C3H8 when written in square brackets will imply its concentration. Okay, so, it is kilomole per meter cube sort of thing. So, this will be kilomole per meter cubed second, because it is a rate, and that comes from a global reaction rate constant multiplied by concentration of propane raised to some power and concentration of oxygen, this is not oxidizer, O2, raised to some other power. Where do these powers come from? Okay, these powers you can get from one of the tables in chapter 5, I think it is table 5.1. So, these are essentially what we have been referring to as M and N, correct? And how have these been obtained? Okay, you get it from table, but how did people get to construct the table? They did a lot of experiments, and then based on those experiments, based on measurements of concentrations at various points of time, they could construct this sort of a reaction rate. Okay, and if you want more detail, you can look up Kg. So, Kg will depend on a pre-exponential factor, it will depend on activation energy. In the table, in fact, it is given in terms of activation temperature, which is activation energy divided by the universal gas constant. And here the only issue that you have to keep in mind is at what temperature do you evaluate the global reaction rate constant, and also what are the concentrations to take, because we understand that in the flame region the concentrations will vary. So, which reaction rate will you take in order to get this omega dot f bar? So, omega dot f is what you see here, omega dot f bar will be some kind of an average that multiplied by a molecular rate will molecular weight is going to give you m dot f triple prime bar, okay, which is the average reaction rate, and that will go into the SL expression. So, I recommend that you look up an example to see at what temperatures you will evaluate Kg, and then at what kind of concentration values you will take for C3H8 or O2 or whichever fuel you have. Okay. And similar comment applies to alpha also. Alpha, for determination alpha, you need K divided by rho u Cp. So, again the question of at what temperature you evaluate K, and at what temperature you will evaluate rho u, at what temperature you will evaluate Cp, these questions will come. So, again look up the example. We will have a little better understanding of this.
So, in example, K and Cp are the mean temperature of product, while the rho u is the at 298. So, why it is so?
Yeah, so this is a little bit of a problem in the sense that it's hard to appreciate why it is like this, because the question here is that K and Cp are evaluated at some temperatures, but rho u is evaluated at the unburnt temperature Tu. So, this is little confusing, I agree, because alpha is not alpha u, alpha is not the thermal diffusivity of the unburnt mixture. For alpha we are using K at some reaction zone temperature, some higher temperature, but for rho u we are evaluating rho u at the unburned gas temperature. So, rho u is at Tu. Now, why are we doing it like this? Because if you go through the derivation, this is how we got alpha. So, we did the derivation, remember we assumed a linear temperature profile, then we integrated it twice to evaluate two eigenvalues of the problem. One was m dot double prime and the other was delta. Okay, m dot double prime of course had SL included in it, and in the process somewhere we got k divided by rho u Cp, we called it alpha. So, even though it is just one quantity alpha, it is not evaluated at a consistent temperature. Okay, so this is the nature of this derivation. It could have been done in some other way. All right, so we don't have the time to get into that. So, I agree it's a little bit confusing, but the good thing is that here we are writing rho u, we are using the subscript u. So, this will remind you that this has to be evaluated at temperature T. Okay. This is not very solid. Okay. This is a simplified derivation, there are a lot of assumptions, it's not very accurate. This gives you a feel of what laminar burning velocity depends on, but it's not exactly accurate. So, we will have to take it in that spirit. Now, fortunately for us, today we are discussing on what parameters laminar burning velocity will depend. How will it depend on pressure? How will it depend on temperature? How will it depend on equivalence ratio? Things like that. Since we are going to discuss these, we will again touch upon some of these aspects, what temperatures to use and things like that. So, again going back to the SL expression, here alpha as we wrote is k divided by rho u Cp, and I will first tell you what the book by Turns does. So, Turns has written alpha proportional to this. So, please hold on for a minute, I will tell you how it comes. Okay, as of now alpha proportional to this. So, let us call it maybe 1, and then we also have m dot f triple prime bar divided by rho u proportional to so that is your number 2. Okay. So, this is equation 1, this is equation 2, actually not even these are not equalities, these are proportionalities. So, proportionality 1 and proportionality 2. So, if we have these two, then once we have got these can be used in SL expression to get dependence of SL on various things, right. So, we use 1 and 2 in the expression for SL. So, if you do that, then SL is proportional to I think I got it wrong, I have to cut this and write it again. Okay. SL is proportional to, actually the last one was also right, but write a more compact form. So, this is after using 1 and 2 in the expression for SL. So, why did turns do all this? Because this now tells you how SL should depend on TU, this tells you how SL will depend on pressure, things like that. We want to see how SL will depend on various things that we understand more easily. We know that SL is proportional to square root of alpha into reaction rate, but then we do not talk about alpha all the time, right? We do not talk about thermal diffusivity all the time. So, we have to talk about things which are easier to understand for us, like pressure and temperature. If somebody asks you if pressure is increased, what will happen to laminar burning velocity, then you should be able to answer this more easily. If we are always stuck with alpha and reaction rate, that is not easy. So, that is why this has been done. Now, we had this 1 and 2 on the previous page. So, we are going to look at that one first, and one was alpha proportional to TU, T bar to the power 0.75, pressure to the power minus 1. Okay, so how did this come? This is 1. Now, alpha is K by rho u Cp. Okay. And we are using, in fact, K and Cp at some temperature T bar, some average temperature in the reaction zone, right? And for rho u, we are using Tu, as we just now discussed, just a few minutes back discussed. So, the question is, how does K depend on, let us say, T bar? So, K, thermal conductivity, is really not strongly dependent on pressure. It depends primarily on temperature, and it is more like temperature to the power half. Okay. Now, this is for gases. For gases, thermal conductivity goes with temperature to the power half, and it is largely independent of pressure. So, if you take that, then this should be, alpha should be like proportional to, because of this K, it should go with T bar to the power half. T bar is some appropriate temperature, it is not Tu. Okay. And for rho u, things are easier. Rho u is the density of the unburned gas, so that should be obtainable in terms of the ideal gas law, correct. So, we will just write this as pressure divided by R bar and pressure divided by, actually no, we do not even need to write R bar, we will write R u. U is not universal, U is unburned, okay, we have to remember that. P divided by R u Tu, that we can write for rho u, okay, ideal gas, because P equal to rho R T, where R is a characteristic gas constant. So, R u is the characteristic gas constant for unburned gas. So, this should be okay. Now, the problem is we also have Cp, and we do not know, I mean, it is no easy way of writing dependence of Cp on temperature, because as you probably all know that Cp will depend on temperature in some polynomial fashion, right, some power, series of powers, added series of powers. So, there is no very simple way of writing this, and this tells you that we expect alpha to be like, it will probably go with T bar to the power something, okay. It will definitely be Tu, proportional to Tu, this Tu, and it will go with pressure to the power minus 1. Now, this T bar has some power, correct. This is what this is telling us, but it is not straightforward to say what this power will be, because Cp has that polynomial expression, correct. So, what do we do? Not very clear. So, if you compare what I have just now done, this red box, and what is there in Turns's book, the blue box, then you will see that we are doing okay, except that we do not know what the power of T bar should be. Actually, Turns has used a power of 0.75, which is a little debatable. Okay, he has used this on some empirical basis. He has looked at the variation of temperature, variation of thermal conductivity of air over some temperature range, and he has done some empirical calculations. And he has actually used 0.75 out there, but this 0.75 is not very convincing if you look at this, because just see what we have here. In order to have T bar to the power 0.75, we will need Cp to go with temperature to the power minus 0.25. Okay, so that's not very convincing. So what is that power going to be? There is no easy way of writing it, but this is some positive number. Okay, most likely it's some positive number. So we'll keep it like this. We'll use 0.75. We'll not keep it like this. We'll use 0.75 because this is what the book uses, and that 0.75 is in fact has given this 0.375. Somewhere there was a root, because SL has a root, no? SL has a root, so that's why this 0.75 became 0.375. So this 0.75 has a question mark. This 0.375 also has a question mark. So we will not go by this strictly, but we will still write 0.375. So when you look at this 0.375, you will think about this as some number which is less than 1 probably, or some positive exponent. That's all. I don't think it's 0.375. Okay, but we'll keep it this way. So this is 1. This is our relation 1. Now there is a relation 2 also. Relation 2 is much better. I'm much more convinced by the relation 2 that has been used in the book. So how do we check that relation 2? Now for relation 2 was for m dot f triple prime bar divided by rho u. So this is our 2, proportionality number 2, and let's see how we analyze this. M dot f triple prime bar is minus kg Okay, so this can be written. Where did I get this from? We just saw a few minutes back that m dot f triple prime bar is omega dot f bar into the molecular weight of the fuel, correct? So from that we can get something like this. Now it still has that kg. Kg must have come from the omega dot f expression from some table. Then we have to use concentrations. Now instead of concentrations, kg expression had concentrations raised to some power, those things in square brackets. So instead of those concentrations, we can write in terms of the mass fractions. So if you write in terms of mass fractions, you should be able to get this. But in addition to mass fraction, you will also end up getting density. Okay. So we'll use an average value of density, we'll use an average value of the fuel mass fraction, and we'll use average value of the oxygen mass fraction. And these powers are N1 and N2. So N equal to N1 plus N2 is the overall reaction order. What is the purpose? We want to bring in pressure and temperature, correct? Because If you look at number 2 is what has been achieved by replacing various things in terms of pressure and temperature. So, we will have to do the same thing again. So, if you do this for m dot f triple prime bar divided by rho u, then the rho u will give you Tu by P dependence. I have now made this a proportionality, by the way. This is a proportionality. This was m dot f triple prime bar. Now it's m dot f triple prime bar divided by rho u, correct? And that rho u has brought in Tu and pressure. And now the extra thing that Turns next does is that he evaluates m dot f triple prime bar at Tb. Okay, there was another option. I mean, those of you who may have looked at the example problems to calculate laminar burning velocity may have seen this, that okay, we have the reaction zone and this is Tu, this is Tb. So, one option is to evaluate the reaction zone, the reaction rate at what temperature? Mean of this temperature and this temperature. And if you take a linear temperature profile, this temperature is half of Tu plus Tb. So, the reaction zone, the temperature that you use for reaction rate calculation was half of this plus this, correct? So, that way you bias the reaction zone temperature, the temperature at which you calculate reaction zone, closer to the burn temperature, but you do not make it exactly equal to burn temperature. But what we just now saw is here the book in fact uses m dot f triple prime bar at Tb for simplicity, just to make expressions easier. So, if you do that, you will get things like this. Correct? How do you get this Tb to the power minus n? This must have come from the rho bar, which is now evaluated at Tb. Okay, the rho bar is evaluated at Tb. So, that will be again ideal gas law. So, that will give you Tb to the power minus n. This thing is n, right? This is n1 plus n2 is n. That is why you get Tb to the power minus n and P to the power n, pressure to the power n. Okay. And exponential this.
So the rho bar was calculated at T bar, average of the.
Yeah, so he's making it further simple. So he's forcing it here. He's saying m dot f triple prime bar is now evaluated at Tb for simplicity, so that we get a more tractable expression. So if you do all that, then you can see that this comes, correct? So that is m dot f triple prime bar by rho u. So we have now got this, which is the same as what I had previously written. So that is how we understand 2. And 1 and 2 used together gave us the expression for SL. So that gave us the expression for SL. Where is it? Yeah. So SL is proportional to Tu All right. So please check this yourself. This has been obtained after using 1 and 2 in the expression for SL. And remember again that this is a little questionable, but doesn't really matter. We will take it to be some positive number, some small positive number. Correct? And apart from SL, you can do a similar exercise for delta. We're interested in two things. We are interested in the laminar burning velocity value, but we are also interested in the flame thickness. Flame thickness is also important. So for flame thickness, we can do a very similar sort of thing. In fact, the proportionality expression that you got for SL will actually help us get the flame thickness also, the flame thickness dependencies also, because we got flame thickness delta as 2 alpha divided by SL some time back, I think in the last class. So if it is 2 alpha by SL, we know how alpha depends on temperature and pressure. Here we have this expression which tells you how SL depends on temperature and pressure. So we can get the dependencies of delta, that is the flame thickness, on various things. So again, 0.375 Tb to the power n by 2 p to the power minus n by 2. Okay. So
Expression also it would be 2 exponential 2.
which one?
In the SL expression, sir, activation energy.
Activation energy is okay, that's correct. That is also 2, and you know why this 2 has come? This 2 has come because of the square root. Okay. And the other thing to note is that since delta is proportional to 1 over SL, that's why this has become a positive thing, a positive number. Okay, because this is negative, this is positive. So that's the other thing that one should note. All right, so this is the groundwork. We'll keep this in mind and then think about if you change various parameters, what will happen to SL. So the first thing that you can think of is that, okay, if you increase unbound temperature, what happens to laminar burning velocity? It will definitely increase, okay, because there is a proportionality here. But unbound temperature will also affect something else. Unbound temperature will affect what else? It will affect T bar. Okay. In fact, it will affect TB also. What is TB? TB is the burn zone temperature. Okay. And if you are asked to get an estimate for TB, what will you do? You can do, as a first level thing, you can do a calculation of the adiabatic flame temperature. The adiabatic flame temperature for a given TU is what TB is like. If there are not much heat loss from the flame, then TB is approximately equal to the adiabatic flame temperature. So adiabatic flame temperature we know how to calculate, isn't it? If there is complete combustion, we know how to calculate adiabatic flame temperature, or more realistically, if you want to use equilibrium, then we have used equilibrium calculators in the past to calculate TB. So for a given TU, we know how to calculate TB. We also understand, it's not very difficult to do that if you increase TU, then your HR, that is the enthalpy of the reactants, is in fact higher, because the sensible enthalpy of the reactants is higher. So if that is higher, then HP is also higher, and then the burnt gas temperature is also higher. So if you increase TU, you are in fact increasing this, but also increasing T bar, you are also increasing TB, and there is an increase in TB here. And we also know that the exponential function is strongly sensitive to changes in temperature. So you increase temperature TU, it will increase TB, and that goes in the exponential term, so that will affect some increase in SL. Okay? Yeah.
What was T bar?
T bar was at TU plus TB for the reaction zone calculation. We have used at some places. We have used
No, so for the reaction purpose.
for the reaction zone purpose. It was half of this one. But for alpha, it was TU plus TB by 2. Okay, for alpha it's TU plus TB by 2. So it's like the mean temperature, the middle temperature of the entire flame zone. Okay. So, there also if you increase Tu, Tb is going to increase, right. So, T bar is also going to increase. So, all these things are going to happen. So, if you increase unbound temperature, laminar burning velocity is going to increase because of all these various effects. Actually, it may not be all that straightforward always, because sometimes if you have very high Tu, then the reactants can also undergo some reactions before combustion. I mean, in the preheat zone also they can undergo more reactions. So, that dissociation effect is actually not taken care of directly in the simplified expression that we had done. Okay. So, it will, if you have very high temperatures, the effect of that pre-flame reactions is not really modeled by this. But overall, we will try to remember this, that if you increase the unbound gas temperature, then the burning velocity is going to increase. All right, what else can we think of? We can also think of the flame temperature, which is very similar. What is the effect of the flame temperature? By flame temperature, at least in these expressions, will mean Tb. Okay, Tb is the product temperature, which is the burnt gas temperature, which is also like the flame temperature. Okay. Now, you might say, what is the flame temperature? How do you know flame temperature? Is it Tu plus Tb by 2? No, maybe we will not include that as the flame. We will not call that the flame temperature. Flame temperature, flame is what, where the most of the reaction is taking place. Most of the reaction is taking place close to Tb. So, the flame temperature is actually close to Tb, maybe a little lower. Maybe it is better to say that flame temperature is somewhat lower than Tb. But we will not make that distinction, because we have already said that the reaction rate is evaluated at Tb. Reaction rate, just a few minutes back, I said that Turns had used this simplification, that reaction rate is evaluated at temperature Tb. So, let us be happy with Tb. Now, Tb, if Tb is higher, again laminar burning velocity will be higher, because the predominant effect will come through the exponential term. Okay. There is some effect of this also. This is with a minus exponent, but this will not be a very strong effect. What is n like? What is the value of n like in practice? N is the overall reaction order. So, do we have some idea of what n is like? Yeah, because today itself we have seen one expression, right. So, actually I wrote m and n, but I think later on he says n1 and n2. So, let us write n1 and n2. n1 is with the fuel. Is he writing n1 for fuel? N1 for the fuel, right? Yeah, N1 for the fuel. So, that is correct. So, this is not M, you can call it M, but let us call it N1. Let us call this N2. So, you can see for the case of propane, single step reaction, overall reaction order is 1.75. So, typically for all these hydrocarbons that we are looking at, reaction order varies between 1.5 and 2. Okay. So, this minus n by 2 that we got out there, minus n by 2, this is just about what, like less than minus 1, isn't it? Less than minus 1. So, this is not such a big effect. Actually, this effect is stronger. Plus, there is positive effect, enhancing effect of Tb through this also, through T bar also. Okay, so we have learned that if you increase Tu, laminar burning velocity is going to increase. If you increase the flame temperature, then also laminar burning velocity is going to increase. Then what about the effect of equivalence ratio? Equivalence ratio is also going to be important. That's actually something very important for us to know, because we are always thinking about whether to burn stoichiometric or to burn lean or to burn rich. We have to make these decisions. As combustion engineer, we have to make these decisions. It so happens that there are some methods of controlling pollution, controlling NOx emission, which use strategies like you burn rich and then you burn lean. You do not go close to an equivalence ratio of 0.9 or so. Avoid some zones of equivalence ratio so that the NOx production is not too high. Okay. So, if time permits, we will get into these strategies, but the point that I am trying to make is that we have to make decisions about rich combustion, lean combustion and things like that. So, we have to know how laminar burning velocity depends on equivalence issue. So, what is the primary effect? You do not see equivalence issue here directly, is not it? We have expression for SL right in front of your eyes, but where is equivalence issue? Not directly, right? Does not show up directly. So, where is it? Yeah, so that is a good point. And we all know how this varies. We know that if we plot the adiabatic flame temperature, we know how to do it. Then we see something like this, where this was slightly higher than stoichiometric, typically. There are exceptions, okay? But typically for most hydrocarbons, this is the way it happens. So, this is more like slightly greater than 1, slightly greater than 1, at that the temperature peaks. And if the temperature peaks, you are likely to get the higher burning velocity at that temperature, okay, again because of the exponential term effect. That is what primarily it is. If you have a mixture which is close to stoichiometric, higher flame temperatures will mean higher burning velocity. And typically also what will happen is that if there is a higher burning velocity, we will expect the flame thickness to be smaller. So, if you have a stoichiometric flame, that is actually very strong, higher temperature, higher reaction rate, high burning velocity, and thin reaction zone. The reaction zone is thin because the reaction is happening fast enough to keep the reaction zone as thin. If the reaction rate is small, if the reaction zone is weak, then it will tend to spread over some considerable distance, okay, some thickness. Well, maybe should not call it considerable, it will still be of the order of millimeter, but or fraction of a millimeter, but this is thicker if the reaction rate is smaller. Okay, so we understand this one. What else? So, we looked at effect of initial temperature, we looked at flame temperature. Now, another important point, of course, is going to be pressure, right? Of course, it is going to be dependent on pressure. So, what you see here in this expression is that pressure to the power n minus 2 by 2. And for typical hydrocarbons, we learned that this n, the overall reaction order, is between 1.5 and 2. So, it is actually less than 2. So, this gives you a slightly negative dependence on pressure. So, laminar burning velocity decreases with pressure slightly. Okay. So, that is one important effect. Again, there are some exceptions, but primarily this is what happens. So, if the reaction order is, let us say, 1.5, n is about 1.5, then it is p to the power minus 0.25. Okay. But that is about as strong it gets, because in other cases if n is more like 1.75 or 1.8, then the effect is even smaller. So, this is the effect of pressure. Now, what else can we think of? We can also think of what will happen to SL if there are some additives. Now, that is a big question to answer, because there can be different kinds of additives, but additives can affect the reaction in the flame. And we will just take one example, because generalizing this is difficult, but if you have, or maybe two examples. One is that if you have non-reactive additives, if you add, let us say, nitrogen or argon to the flame, what will you expect to see? So, instead of the fuel, if let us say you add some diluent to the fuel, what do you expect to see? SL would decrease. Okay. By diluent, I mean some inert gases which are not participating in the reaction. So, if we add nitrogen, for example, or if you add argon, then that will dilute the concentration of the fuel in the reaction zone. So, the reaction rate will come down and laminar burning velocity will come down. CO2 can do the same thing, but CO2 can actually affect reaction rates in some way, because in hydrocarbon combustion we understand that carbon dioxide will get produced, right? Carbon dioxide will get produced as part of the combustion process. All right. We understood that hydrocarbons will break down and then it will give you various radicals. Remember the 8 steps which we looked at for hydrocarbon combustion some time back, and in the process somewhere it will give you carbon monoxide, and then that carbon monoxide is also going to get converted, oxidized to CO2. So, if we're adding CO2, maybe you will affect some reaction rate also. So, CO2's effect is little more complicated than typically the effect of, let us say, something like argon. But CO2 will also typically reduce the reaction rate. So, burning velocity will decrease. Now, this is one aspect. The other aspect, one more example I want to take, is that what happens if you add moisture to, let us say, a carbon monoxide flame. So, again we have learned something about carbon monoxide oxidation. So, that will tell you what might happen if you add carbon monoxide. If you add moisture to a carbon monoxide flame, what will you likely to get? Reaction rate will increase and the laminar burning velocity is going to increase. So, the data that I have is that if you have CO-O2 mixture and absolutely dry, and if you add, so to this CO-O2 mixture you are adding 0.23% water vapor. So, the burning velocity increases by a factor of 8. CO2 mixture at 0.23% water vapor. This is I am quoting 0.23% because there is data, but somebody has done this experiment, that is why. So, 0.23% water vapor, then the burning velocity, laminar burning velocity increases by a factor of 8. Okay. So, this is a situation when you have added something and then that is really increased burning velocity. All right. Now, I have not done something which you need to do, whether I have not shown you actual data. So, if you go to the book, Turns's book, chapter 8, there are plots which will show you how laminar burning velocity increases where unburnt temperature is increased, how laminar burning velocity varies with equivalence ratio, how laminar burning velocity for methane decreases with pressure, things like that. There are some plots using actual experimental data. Okay. So, I have not shown you that, but that I leave as homework for you. You can look that up. Now, there is another thing that I want to ask you to look up on your own. That is, Turns writes this as flame speed correlations. I think some of you may have already seen this, flame speed correlations. So, these are available in the book because people, different researchers have done experiments with fuels like propane, isooctane, and then there is also, I think, some other fuel which people have looked at. So, for these fuels they have got pressure, they have got they have done experiments at various pressures and temperatures and measure burning velocity, so under various conditions. So, how do you define a mixture? You have a particular pressure, you have a certain temperature, you have a certain equivalence ratio for the unburnt mixture for a certain fuel, then that defines a mixture. Now, for that mixture they have measured burning velocity, and that burning velocity has from the burning velocity of data, they have constructed correlations, and those correlations involve things like pressure, temperature, equivalence ratio, things like that. In fact, some of these experiments have also been done with inert gas. Some of these experiments have the effect of diluents. Diluents are inert gases like I mentioned, argon or nitrogen, affecting the flame. So, you will see that okay, if there is a certain percentage of diluent in the fuel air mixture, then how to calculate burning velocity. So, that is also something which we did not directly discuss, but these correlations will allow you to calculate laminar burning velocity for various kinds of mixture conditions, including diluent concentrations. And one good thing about these correlations is that these are available for various pressures, in fact, and for some high pressures also. Typically, the problems that we solve in classroom and problems which are given in textbooks are at 1 atmosphere, typically. Okay? And the example problems which I asked you to look up, those are also at 1 atmosphere. But if you think about, let us say, a spark ignition engine or a gas turbine, pressures are higher. Okay? In fact, as an exercise, please look up what is the range of pressures in SI engines, what is the range of pressures in gas turbines. That will be a good thing for you to learn. Okay? This will give you this practical aspect which you need to know, because in classroom sometimes we are just doing more theory and derivations, but you need to know this also. But these pressures are always higher. So, the flame speed correlations which are given in Turns' book, they give you at least for some limited range of pressures, laminar burning velocity values. Now, I must clarify again, what Turns means by flame speed is what we are calling at SL. We are calling SL laminar burning velocity. So, we are not using exactly the same terminology at Turns. And according to what I prefer to use, flame speed is the spatial speed. This is SS. Long time back we looked at this, spatial speed. Okay. So, when he writes flame speed correlations, we will think about this as laminar burning velocity correlation. Okay, so this we will do, and the other topic that we will not be able to do today, but we will touch upon and pick up in the next class is quenching. So, we learned something about laminar burning velocity, which is a fundamental property of a fuel air mixture. Okay, laminar burning velocity is a property of a fuel air mixture, because I told you that okay, if you change configurations, if you change geometry, if you change flow rates, as long as the flow is laminar, okay, within the laminar range, if you change the flow rates, does not matter, SL is going to be one single value. All right. So, that is why it is a property, that is why it is so important. But we cannot stop there, we have to look at some other phenomena also. So, the next phenomena, we are studying premixed combustion. So, other phenomena which are important to premixed combustion, we will also discuss, and one of them is quenching. So, the problem that we will discuss is the following. Suppose you have two walls, and between these two walls, so you are looking at it from this direction, you see these two walls, and you have this fuel air mixture here, and you get a flame. So, the flame is like this, all right. So, I am showing the thickness of the flame. So, that means this should be, in our terminology, what should I call this? Delta. Okay, so we call this delta. Okay. We call this one distance between the two walls, which is d, and we will call this as some L. Okay. So, there is a fuel air mixture between the two walls, and then the flame, we got a flame, and the flame is propagating. Now, remember that we had seen some videos, not of this kind of situation, not exactly this geometry is two walls, but we have seen tubes, and we have seen tubes of different diameters, and we have seen that in some cases the flame is not able to travel long. for long duration. So, it travels a little bit and it gets extinguished. We remember that video. Okay, so it is possible, if you look at this, it is possible that if the distance d is small, correct, d is in your hands, you whether you keep the two walls far from each other or you bring the two walls close to each other, that is in your hands. So, if you do that, if you make d small, then the experimental evidence which we had seen in that video tells us that the flame may not propagate, correct. But we did not have a detailed discussion on this. So, we will have to think about, in the next class, we will think about what is it that might result in the flame getting extinguished, and can we calculate, can we develop an expression for this distance d, which will result in the flame not being able to propagate. From what we could understand from that video is that the flame will propagate if the distance between two walls is large, isn't it? And if the two walls are close to each other, or in the example of the video, narrow tube, if you have a narrow tube, then you are more likely to get the flame getting extinguished. All right. So, we will think about that video. If possible, you can have a look at that again, and then come to the next class, and we will try to think about under what conditions it will get extinguished and derive an expression for d. Okay. So, we will stop here. Thank you.